talk about is untwisted multilayers of graphene. They also show somewhat reminiscent but very, very rich physics, and also multilayer TMD systems. And okay, so these systems, compared to more traditional bulk quantum materials, have some new features. So they have multiple valleys. They have interesting dispersions. They have all sorts of superlattices that can be controlled very, very precisely. Their band structures are often topological, and that brings a new aspect to this physics. And of course, that leads to extremely rich phenomena that is observed. Okay, all kinds of new types of generalized ferromagnets, spin and valley and orbital ferromagnets, correlated insulators, superconductivity, and both integer and fractional churn insulators, and so on. Okay, so it's a very, very rich arena that we really didn't have 6 years ago, and it offers really new tools, new levels of control of quantum materials, and I'm going to focus on these systems as a laboratory for studying superconductivity. Okay, so the theme of all these talks would be, here's a system where we really know quite well what the Hamiltonian is. We can even control it to a large degree. We have this really spectacular level of control, and it is a superconductor. Can we really pin down the superconductor? Okay, just as a test to our theories, to our understanding of superconductivity in general. Okay, so this is sort of a rough outline. Okay, that might evolve over time, but I'm going to discuss superconductivity in rhombohedral graphene multilayers. So far, it's been discovered in bilayer and trilayer. Stefan, who's here, will tell you more about experiments in bilayer, I think. Okay, so I'm going to give you I'm going to review briefly the experiments. I'm going to give you the theorist's view, and I'm going to focus on what I think are interesting puzzles related to superconductivity in these systems. I think the problem is far from being solved. It's really an open problem. I'm going to take the point of view that maybe the mechanism is an electronic mechanism, and discuss the consequences of that. Okay, and probably next time, next lecture tomorrow, I'll talk a little bit about spin-polarized triplet superconductors, which is a form of exotic superconductivity, which is definitely observed in these systems, and that's by itself is new, and that's pretty well established, I think, and some of the consequences of that. And if time allows, maybe I'll talk a little bit also about spectroscopy of collective modes of the superconducting state in these systems and what that could teach us. Okay, so that's the rough plan. I don't have to go through all of it, so please, again, interrupt me at any point. Okay, so I'm going to start with the band structure of these systems that I'll be discussing. Okay, so bilayer and trilayer rhombohedral graphene. Okay, so as you may know, you just take 2 layers of graphene. They like to stack in this form called Bernal stacking, which just take 2 of these layers. The A sublattice of the honeycomb lattice of one graphene sheet is just below the B sublattice of the other one. Okay, and this is the stable configuration of 2 stacked layers of graphene. If you take 3 layers, actually the natural stacking would be A, B, A. Okay, so we would like the A sublattice of the bottom layer to be aligned with the B sublattice of the next layer to be aligned with the A sublattice again of the layer above. So that's one possible stacking. That's the stable configuration called ABA. But there's a metastable configuration, which is called rhombohedral trilayer graphene, which is ABC. Okay, so this is what the unit cell looks like from the side view. Okay, so relative to the stable configuration, you basically shift the upper layer by by basically half a unit cell. Okay, and it turns out that this configuration for the purpose of correlated electron physics and superconductivity is actually the more interesting one. You'll see in a moment why. And this actually extends. So if you just continue stacking more and more layers, okay, so the stable configuration would be eventually graphite. So that would go A, B, and so on. But you have metastable structures of this form. So ABC, and so on. That's rhombohedral graphite. So it's these are all metastable, and that of course makes them harder to work with. But people know how to fabricate these things, and actually people fabricated 7, 8, 9 layers of rhombohedral graphite. And once you manage to produce such a sample of rhombohedral graphite, and you encapsulate it by a substrate from both sides, it's metastable. It can live for a very long time. Okay, so what makes these rhombohedral structures interesting? What makes them interesting is that they actually have a very high density of states, okay, relative to the graphite, and that of course is very conducive to correlated electron physics. Okay, so I want to walk you a little bit through how to understand the band structure here. Okay, so the first observation is that take this example of the trilayer. The important orbitals that are living close to zero energy are living mostly on the A sublattice of the bottom layer and the B sublattice of the top layer. Okay, and why is that? That can be understood very simply. So think about the electronic structure of a single graphene sheet. So you all know that's a Dirac spectrum, which is where the Dirac point is exactly at the K point. So at the K and K prime point, center of the two valleys, you have these two bands that touch each other. So let's do a K dot P expansion around that point. Okay, so if we expand around that point, so now we're gonna, that's a single graphene sheet. Now we're gonna turn on the interlayer hopping. Okay, so before the hopping, we basically have these two states at each valley, which are degenerate, and their wave functions can live. You have two degenerate wave functions that live either on the A, on the B, or the B sublattice. These states are degenerate before the interlayer hopping. Okay, and now we turn on the interlayer hopping. So what's going to happen? Okay, and this is a large energy. This is around 100 millivolts. What happens is that the states that live on the B sublattice of the top layer hybridize with the A sublattice of the layer above, and they get pushed of order 100 millivolts away from the Fermi level. And same for the state of the B sublattice of the second layer, which hybridizes with the A sublattice of the layer above. They also get pushed very, very far from the Fermi level. Okay, and what remains close to the Fermi level at this sort of first order perturbation theory at the K and K prime points are these states, which are living on the A sublattice of the bottom and B sublattice on the top. Okay, so these are the states, these are the important states that would consist of most of the wave functions close to the Fermi level, close to zero energy. Okay, and so we can write an effective 2x2 Hamiltonian. Okay, we start from 6 orbitals per unit cell. We end up with only 2. Okay, the effective Hamiltonian would have this this sort of form. Okay, so what are these terms? So you can already see that the very important knob to tune the system would be a perpendicular displacement field. Okay, because of the fact that the wave functions at the K and K prime valleys. Okay, so this is the Brillouin zone of graphene. We're interested in states at low energy, which are living close to the K and K prime valleys. These states would mostly be localized on the A sublattice of the bottom and B sublattice on the top. So they would respond very, very strongly to a perpendicular displacement field that would polarize the states either to the bottom or to the top. This system is extremely polarizable. So there's a potential difference between the bottom and the top layers, which are called here delta 1. Okay, and that's proportional to this displacement field D that you can apply by just having a dual gate. And so that's the diagonal part. That's just a potential difference to delta 1 between bottom and top. And you can hop from here to here, okay, from A1 to B3, you can hop, but that hopping process, okay, so that requires you basically to go through these high energy states that are split away from zero energy by the interlayer hopping. Okay, so so basically you have for the trilayer, this is the example of the trilayer, you can hop from A1 to B3 to third order in perturbation theory in K, which is the deviation from the center of the valley. And this is why you get, at this level of approximation, you get this cubic term on the off diagonal. Okay, so that's this cubic term. Okay, so kx plus I tau. Tau is the valley index, k or k prime, plus I tau times ky. That term is simply the kinetic energy of a monolayer graphene, and you have to apply that 3 times to get to the B sublattice of the other layer. Okay, and so that's one term in the Hamiltonian. If you just solve, it's actually a great exercise. If you just solve this tight binding model and expand the dispersion close to the k and k prime points, that's actually what you'll get. You'll get this cubic dispersion. If delta 1 is 0, the dispersion would actually go like k cubed close to the k and k prime points. And in addition, there's this gamma term, which is a trigonal warping term. Okay, so if you neglected this gamma, you would have a completely rotationally symmetric dispersion around the k and k prime points. Trigonal warping comes in through this gamma term and retrieves the C3 symmetry of the underlying lattice. Okay, but you already see why there's a high density of states. Okay, so if delta 1 is equal to 0, if you neglect gamma, you get a cubic dispersion instead of graphene's linear dispersion. For bilayer, for the Bernal bilayer, you get a quadratic dispersion. And if you continue adding rhombohedral layers, you would actually get k to the power n, where n is the number of layers. Okay, so you get a more and more flat dispersion. These states that have this flat dispersion are living mostly on the top and the bottom layers. They become sort of surface states in the limit of rhombohedral graphite. Okay, and now if you add this displacement field, what that does is that it opens a gap. Okay, so there's a band touching which is nearly cubic. Okay, the trigonal warping actually distorts that. That separates the cubic band touching into 3 Dirac points. But once you add this delta 1, that opens a gap, which is just basically proportional to delta 1. And at the bottom of the conduction band, at the top of the valence band, you actually get an even more flat dispersion. Okay, so that's why this is such a useful tuning knob, and this is why these systems are sort of a natural place to look for correlated electron physics. Okay, so let me show you some pictures of what the band structure actually looks like. This is a cut through the dispersion through the K point. Okay, so one of the valleys, and the black here is without a displacement field. Okay, so there's no cubic band touching because of the trigonal warping. Okay, so what happens is that instead of a cubic band touching, you actually get 3 Dirac points, and this cut is just cutting through one of these Dirac points. But once you add this displacement field, you get this dispersion in blue. Okay, so you get this gap, which is twice delta 1. And you see that you get a very, very flat dispersion for a certain region of K-space. Okay, for the bottom of the conduction band and also the top of the valence band, they're not particle symmetric. Okay, and indeed the phase diagram would not be particle symmetric. But and this is the corresponding density of states as a function of energy for this single particle model. Okay, so you see very clearly these peaks in the density of states. These are von Hove singularities. In the black, that's without displacement field, and once you apply a displacement field, you see this very, very large peak, which corresponds to this flat region in K-space here. Okay, and the same for the valence band. Okay, so the Fermi surface actually has this interesting evolution as a function of density. Okay, so this is on the whole side. This is on this side. Okay, so at very small hole density, you get these 3 isolated pockets. They grow as you add more and more holes. At some point, they touch each other, and you get the Fermi surface, which is this annulus. Okay, and as you add more holes, the outer Fermi surface grows, and the inner one shrinks until the inner one disappears. Okay, and you get just one simply connected Fermi surface. So that's the evolution on the Fermi surface on this side. The Van Hove singularity, this peak, is exactly the point where these 3 pockets touch each other. That's a Van Hove singularity in 2 dimensions. So there's a logarithmic divergence of the density of states there. Okay, so now you might expect that if we place a hole density, which we can control by a gate, if we place that somewhere, close to this peak, the density of states would be very high, and interactions would become dominant, and something interesting might happen. Okay, so the system, the normal metallic Fermi liquid would become unstable, and the system would prefer to do something else. That's sort of a general expectation. That's been noted very early on. Okay, so when people started looking at these systems, but all this rich physics was actually only starting to be realized a few years ago. Okay, so what does the system do when you actually tune the density close to one of these pronounced peaks in the density of states? Okay, so here's an experimental phase diagram from Andrea Young's group for the trilayer. Okay, I would mostly show data on trilayer. I'll show a little bit of bilayer. Stefan would show more. Okay, but at a broad brush level, they're quite similar. Yeah, there was a comment? No. Okay, so what's this phase diagram? So the axes here are density and displacement field. So this is a system with a dual gate. Okay, so you can independently control the density, which is sort of the average voltage on the top and the bottom gate, and the displacement field, which is proportional to the difference in voltage between top and bottom. Okay, and you can translate that into density and a displacement field. And the quantity that's measured here is inverse compressibility. Okay, so this is basically capacitance. It's basically capacitance from the gates to the system. How much charge goes in when you change the voltage? So that's a thermodynamic measurement. It's a thermodynamic quantity that characterizes the system. Okay, and you see these. So for a non-interacting system, this would be basically the inverse of the density of states, of the single particle density of states. For an interacting system, it also includes it's affected strongly by the effects of interactions. Okay, and you see these strikingly sharp features here. Okay, so for instance, these very bright lines, which are negative. Okay, so that's a decrease in the inverse compressibility. It's an enhanced compressibility. Okay, so now I want to confuse you all. Okay, so this is compressibility. It's a thermodynamic response. How can that be negative? Okay, you'll hear this jargon maybe in the field. People talk about negative compressibility. That doesn't make any sense. Compressibility should always be a positive quantity, but that's the jargon. That's what could you do? Okay, you can ask me more about it later. Let's just say there's actually a big constant that you subtract from. Okay, so the actual capacitance is positive. The system is not unstable. Negative compressibility on this plot doesn't mean that the system is unstable. It's just a jargon. It's just a drop in capacitance. Okay, so but what's actually going on here? What happens in this sharp line? Well, it turns out that the fermiology of this state can be mapped to extraordinary detail using quantum oscillation. So we actually know quite a bit about what's going on in this phase diagram. Okay, what these sharp lines correspond to are phase transitions, where the degeneracy of the Fermi surface, which in the normal metallic state should be 4. Okay, so every case state should have should be fourfold degenerate. That's 2 spins and 2 valleys. What happens in these along these sharp lines is that there are phase transitions where the system breaks the spin and valley symmetry spontaneously in various ways. Okay, so for instance here, on the electron side, at the finite displacement field, you actually start from a state where you only choose one flavor out of these four. Okay, so you start from a fourfold degenerate system, and instead of filling everybody equally, you choose spontaneously one. Now that one can be, say, valley k and spin up. That can be a superposition, k plus k prime and spin up. And it can be various combinations of these. Okay, and which one is an interesting question for which there's also quite detailed answers. But at this level, let's just say you just choose one. Okay, and then when you increase the density further, you have this sharp transition. That's actually a first order transition to a state where you choose two out of the four spontaneously. And again, these two could be k with spin up and k prime with spin up. That turns out to be the answer. Actually, you can answer that experimentally. Which combination of spin and valley do you actually choose? But a priori, it may have been k up and k prime and k down. Right? That's also a logical possibility. And finally, when you increase the density even further, you have another first order transition where the fourfold degeneracy is actually recovered. Okay? Yes? Yeah.
Right at just the gravity point, or extremely close to just the gravity point.
Yes.
Do you expect that the order already broken?
Yeah. So the answer is it depends. Okay. It's probably different from for electrons and holes. So this electron-hole asymmetry, you saw that the sharp peak in the density of states for the electron side is almost exactly, of course not exactly, but almost at the bottom of the conduction band. Whereas on the hole side, there's a region where the density of states is lower, and then it grows. And indeed, I mean, on the electron side, it looks like the symmetry is broken right away, and the whole side, there's a region where it's unbroken, and only then it goes into this one fold. Yeah. There's another interesting question here, by the way, that I won't answer. I just want you to think about it a little bit, and maybe we can discuss it further in the discussion. So, people have been studying the 2D electron gas problem for 100 years. And so simple 2D electron gas with parabolic dispersion, we know what's supposed to happen. So as a function of density, which translates to the RS, the Wigner-Seitz parameter, which is basically just the ratio between the Coulomb interaction and the kinetic energy per electron. Okay, and one way to think about the system is it's another kind of 2D electron gas. Okay, so remember, there's no more lattice here. You can basically think about electrons in a continuum with a funny dispersion and with four flavors. But other than that, it's just a strongly interacting 2D electron gas. Okay, and you can estimate what is RS, what is this Wigner-Seitz parameter, the ratio between kinetic and potential energy, and it's somewhere between 6 and 10, usually, for these systems. Okay, so it is a strongly correlated material for sure. Okay, the potential energy is actually bigger than the typical kinetic energy. But we know, for instance, that the 2D electron gas for RS equals 10 is actually a stable Fermi liquid. Okay, it eventually becomes unstable when RS in 2 dimensions is maybe 30, but and it's unstable not to a ferromagnet, it's unstable to a Wigner crystal. Sorry?
So it's not 2 transitions close to ferromagnet, then
That's debated as far as I understand. I mean, yeah. So I mean, I think both experimentally and theoretically, it's not quite settled. But the debate is whether there's a little sliver of ferromagnet before the Wigner crystal or not at all. Okay, but that's all close to 30. That's right. So what's different about the system? Okay, why is the system so strikingly different? So maybe there's some signature of some kind of incipient Wigner crystallization going on here, but most of this phase diagram seems metallic. Okay, no Wigner crystal anywhere. Instead, you get the sequence of generalized ferromagnets, spin and valley ferromagnets. Okay, so That's what this system does, and we can discuss maybe why, but of course, yeah, I don't think there's a definitive answer to that. I think it's an interesting open problem. Okay, so how do we know all of this? How do we know what's the degeneracy of each one of these states? And even further, how do we know which of the 4 flavors are chosen, are selected for each density and displacement field? So there's a very powerful tool here. Okay, the point is that the system is extremely clean. The mean free path of electrons is huge. It's typically microns. Okay, so you see a very pronounced quantum oscillations when you apply a perpendicular magnetic field. And using that tool, you could really map out this phase diagram. This is what was done. Okay, so that tells you, so you pick out the frequencies in quantum oscillations. That tells you the areas of the different Fermi surfaces. And by matching these areas to the total density, you can also deduce what's the degeneracy of each one of these Fermi sheets that you pick out. Okay, so that's how you get all this detailed information about the different degeneracies and further even the different topologies of the Fermi surface. Okay, so this is the whole side of this phase diagram. And so this is the topology and degeneracy of the Fermi surfaces in each one of these regions that you see there. Okay, so in region number 1, which is here, okay, what you see is really a frequency, a single frequency in quantum oscillations, Shubnikov de Haas, which corresponds to 1/12 of the total density. Okay, so to match the total density that you know just by the gate voltage, you have to multiply this frequency by 12 to get to the total area in K space that encloses all the electrons. And that simply corresponds to a Fermi surface for each flavor, which is these 3 degenerate pockets related by C3. Okay, so 3 pockets times 4 flavors, it gives you 12. So this frequency should be 12-fold degenerate, and that exactly matches the total density. Okay, and then you go to this region number 2 here, where the Fermi surface is totally different. Now in each valley you have this annular Fermi surface. There's an outer Fermi surface of holes and inner Fermi surface of electrons, and that's 1-fold degenerate. Okay, so what you see here is just 2 frequencies corresponding to these 2 Fermi surfaces, and to match the total density you need to take the outer one minus the inner one. Okay, so you know that there are only 2 volume or areas of Fermi surface. Each one is 1-fold degenerate, and one is holes and one is electrons. Okay, so you can really read out, ideally, all this information about the structure of the Fermi surface from this evolution of the quantum oscillations. So yeah, I mean, for me, this is really striking. I mean, we've never seen such detailed information about the correlated material from experiment. It's quite astonishing. Okay, and theoretically, a very, very simple model can serve at least as a starting point to understand all this rich physics, which is simply a Stoner model. Okay, so what's the important ingredient? It's basically exchange physics. It's basically an interplay between the density of states, single particle density of states, and exchange. Yes?
Just, I want to make sure it's clear in my mind. This Fermi surface evolution in the lower left, you're saying that from Shubnikov to Haas oscillations, they've been able to determine that the pockets are at least as the size as you show in the diagram.
Yes, yes.
So they get shifts in frequencies.
Yes, yes, yeah,
Okay.
yeah, exactly, yes. Okay. So, right, so this is a sort of 0th order, really, really simple model that has only 2 ingredients. It has the single particle density of states, okay, that from the band structure model that I've shown you before. And it has an exchange interaction, which is a repulsive interaction between the different flavors. Okay, so exchange likes you to have as many electrons as you have in a single flavor, either valley or spin. You gain energy from Pauli exclusion. That's the basic underlying physics behind all of this complex phase diagram. And if you only had this exchange term, which is okay, so it's the density at flavor spin and valley alpha times density in a flavor beta for alpha different than beta, that term by itself would not distinguish different spin and valley polarized states. Okay, if you have a 2-fold state, for instance, you don't care if it's spin polarized or valley polarized or something in between. You just pick 2 flavors. But there's another interaction that I'll discuss quite a bit later, which is called the Hund's interaction, that actually distinguishes these different possibilities. For instance, this term is the spin at value k dotted into the spin at value k prime. And if this coefficient j is positive, that favors spin ferromagnetism over valley ferromagnetism. Okay, so that's another ingredient that you need in order to match, at least qualitatively, this phase diagram. And this is just a calculation from this simple model of the inverse compressibility, and you see these first order transitions. You go from one flavor to 2 flavors to 4 flavors, and here it's symmetry unbroken. Okay, so the basic physics is probably just that, and then there are a lot of details on top of that, but even this kind of really simplified model captures at least to 0th order. Okay, so so there's somewhat similar phenomenology seen in magic angle twisted bilayer graphene. This cascade of transitions between different spin and valley symmetry broken states associated with these sharp features in inverse compressibility are also seen there. A lot of the details are very different because that's a very different system. But at least from afar, this is somewhat reminiscent of that system as well. Yes? There are, yeah. So, good question. Okay, so on the electron side, the way I've described it is that you really go between fully polarized states, one-fold. So you never partially fill one flavor and partially another flavor. You choose one flavor and put all the electrons there and push all the other ones and empty them. On the electron side, that's the case. On the whole side, it's not the case. There are partially polarized phases in between that I didn't highlight here. You can call it that, yeah, yes. Yeah, so it's all coming, I mean, you saw the dispersions. The dispersions are not nearly particle symmetric. It's probably just has to do with the details of the dispersion. Okay, other questions?
So in bilayer graphene, for example, these would take place, the transition would take place at the integer fillings of the flat band. So
Close to integer.
Close to the integer.
Yes.
I know this is a different setting, but
yes.
So the densities where these take place is, although it also depends on the displacement.
Yeah,
is there any
yeah. So I can answer in the model. Okay. In the model, it's the Stoner criterion. Okay, because there's nothing else here. When the density of states times the interaction is order 1. So you saw these, remember these sharp features in density of states. Okay, so suppose you start decreasing density. Okay, from here, the density of states is low. So the symmetry unbroken state is stable. You increase density more and more and more. At some point, before you reach the Van Hove singularity, you hit the Stoner criterion, and that's in the model. That's where these densities, yeah.
Is there any evidence for multi-order in?
There is. I think that Steven would talk about that more in bilayer. Yeah. In the theory, not in this very simple model, in experiment. In trilayer, not direct. In bilayer, there is more direct. It's from quantum oscillations, so it's not quite what we'd like, but yeah. But it's definitely something you expect. So, yeah. So these are all flavor symmetry breakings. You can also imagine spatial symmetry breaking. So, for instance, it's kind of maybe easiest to understand in this regime. So, suppose you have three degenerate pockets. You can gain some exchange energy by instead of filling them symmetrically, just putting all the electrons in one pocket. Okay, and that state breaks the C3 symmetry of the system spontaneously. It doesn't break any flavor symmetry, but that's also a very natural state that one would expect. And at least in bilayer graphene, there is actually pretty compelling evidence that that's occurring. We expect it to be very, very common. It's just the quantum oscillations don't necessarily detect that. You know, if you see only a single pocket, see a single frequency, you actually don't know where that pocket is. Okay, so what you should look for is some anisotropy, say, in transport, and that's not been detected so far. Okay, but yeah, I hope Stefan might talk about it more, or you can ask me. Yes. Okay, so in the theme of this school, okay, there's also superconductivity, and that's what I'll mostly focus on in these lectures. Okay, so it's actually superconductivity is quite prevalent in these systems. So this is it was first discovered in ABC trilayer graphene with hexagonal boron nitride substrates. And this is the same phase diagram now in transport on the whole side. Okay, so this is hole density and displacement field. So you see features associated with all these phase transitions in transport. Okay, the color scale here is just resistance. But you also see these cyan slivers where the resistance drops. Okay, in this region SC1, it's actually dropping to 0. In region SC2, it's dropping not quite to 0, but we still believe that that's an incipient superconductor, okay, just not homogeneous. Okay, and actually shortly afterwards, it was discovered that also the bilayer is superconducting. Superconductivity is strongest when you put the bilayer on WSE2, okay, and a different substrate that, among other things, is inducing spin-orbit coupling. Okay, here all the elements are light. There's a very weak spin-orbit coupling. By the way, weak but not 0. It's measurable, and I can happy to discuss that. But here, spin-orbit coupling induced by proximity from the WSE2 is much stronger. Yeah, there's a question?
Sorry, maybe you'll address this later, but you mentioned that there's superconductivity that you believe is inhomogeneous or incipient. And at some point, I'd like you to discuss just, because these look like these are high mobility samples.
Yes.
What that means and why you would expect that kind of thing to happen in such a system.
Yeah. Okay. So yes, it's a good question. What's exactly the nature of disorder here? I don't know. Yeah, I mean the mobility is definitely very high, but apparently the system is still not completely homogeneous. You see that this is such a narrow sliver, right? It doesn't take much disorder to sort of get you out of the superconductor. I think it must have to do with that, but I don't think it's known what exactly the nature of the disorder in the system. But let me make a comment about that. Okay, so early on, right, I mean, after we were all excited about the discovery of superconductivity in twisted bilayer graphene, there were lots of claims of superconductivity in various other two-dimensional systems that then turned out to be not superconducting. Okay, so this can be quite tricky. You see a drop in resistance that can be due to various reasons, and I think that people developed sort of more stringent tests for superconductivity. For instance, seeing a Fraunhofer pattern when you apply a perpendicular magnetic field, that it does come from inhomogeneity of some kind, but you see oscillations in the periodic oscillations in the resistance, and that's actually observed in these systems. So I think it's pretty established that these are really superconductors. Okay, so some of them are stronger than others, some of them are weak, but this is real. Okay, I think this is now beyond doubt. Yeah.
You agree with spin-orbit coupling, and you definitely need much larger electrical fields for the superconductor.
Yes, yeah. So at least to some degree, the fact that you need a bigger displacement field in the bilayer is to be expected. Just the active layers are the outer layers. So to get the same potential difference between the top and bottom layers, you just need a larger displacement field. Okay, so that's at least part of the reason. Yes, but that's yeah. If you go to more layers, you need a lower displacement field. I think that's at least part of the reason. Now, there's a very important zeroth order question that I don't have a good answer to. There are various theories. Why does spin orbit actually help superconductivity so much? That's a dramatic effect. So here the maximum TC is 100 millikelvin. Here it's 400 millikelvin. And moreover, okay, if you don't have spin orbit, or you have a very weak spin orbit, if you put Bernal bilayer on HBN, it turns out that even without spin orbit, that can be superconducting, weak superconductivity, but it can be superconducting if you apply an in-plane field, which is even more striking. Okay, so usually a magnetic field kills superconductivity. Here it's an in-plane field. Okay, so no, presumably a weak orbital effect, mostly Zeeman, but just polarizing the spins helps superconductivity. Okay, so spin orbit coupling is polarizing the spins in one way. It's polarizing them oppositely in the two valleys, but polarizing nevertheless. And the in-plane field is polarizing them parallel to the plane, in the same direction in both valleys, but both of these things somehow boost superconductivity. Okay, some other characterizations of superconductivity in these systems. Okay, so TC, as I mentioned, the lower ones, you see these different superconducting phases. The lower ones are maybe 30 or 40 millikelvin, and it goes all the way up on these WSC2 substrate systems to 400 millikelvin. Okay, in the samples with low spin orbit coupling. Okay, so when you put the graphene on HBN, we can distinguish, presumably at zeroth order, there's spin SU2 symmetry. We can distinguish singlet and triplet superconductivity, and you can ask which one is it. Okay, so which one is it, singlet or triplet? And it turns out that both singlet and triplet are observed. Okay, so in this system, okay, ABC graphene, there's SC1 that seems to be Pauli limited for an in-plane field. Okay, so it gets killed with an in-plane field approximately where you would expect on the basis of the Pauli limit. Okay, that ends up being 100 millitesla or so. Whereas SC2 is not Pauli limited. It exceeds the Pauli limit by a huge amount. In fact, it exceeds the Pauli limit by at least tenfold, and it's not even decreased by then. And that's actually something you would expect for SC2, because the normal state of SC2, the state above TC, is a spin ferromagnet. Okay, the normal state is already symmetry broken, and it's actually what's called a half metal. There's only one spin flavor at the Fermi energy. So there's only one spin flavor to pair. So naturally, that's what you get. You get that spin flavor is paired. Okay, so and moreover, in this AB graphene with an in-plane field, of course, the spins are fully polarized. It's, so this clearly is triplet. So both triplet and singlet can be realized, and I'll discuss that a little bit later. Okay, so finally, you sort of observe, you can maybe see that superconductivity occurs, tends to occur, not universally, but tends to occur right at the boundary between two regions with different contrast. If you go back to the phase diagram from before, it turns out that superconductivity sort of likes to live, for some reason, right at the boundary or at the cusp of some symmetry breaking phase. Okay, it's so you see here SC1, for example, that's living right at the boundary between this phase, which was the fourfold symmetry unbroken phase, and this phase, which is actually some kind of partially polarized phase. Okay, so over here. Okay, so yes.
These are all first order phase transitions.
So not all of them. This phase transition is first order. Yes, so it's first order. We can argue how strongly or weakly first order it is. In the first experiment, they actually couldn't resolve whether it's first or second order, but in a more precise experiment, they could detect a small jump in chemical potential. Okay, so yes, so these transitions are mostly first order. Some of them more weakly, some of them more strongly. Okay, so these are some observations. Here's another one, which is I think is important and interesting. So these superconductors are really deep in the clean limit. Okay, so we know what we have an estimate for the mean free path. The mean free path is several microns, or actually of order of the sample size, and we know what the coherence length is from the out of plane critical field, and this ratio of mean free path to coherence length is at least 10. And in the systems with higher TC, it's even bigger. Okay, and why is that important when you think about when you start thinking about mechanisms? So you know that for anything but S-wave superconductivity, non-magnetic disorder is a pair breaker. So if this was the other way around, it would be very likely that this is some kind of conventional S-wave. But this means that other possibilities are not ruled out as of yet. Okay, and something nice to have in mind is this beautiful example of strontium ruthenate 214, the monolayer strontium ruthenate material, which is a superconductor, which is extremely sensitive to the presence of non-magnetic impurities. Okay, so this is a sort of classic experiment by Andy McKenzie and collaborators. So they introduced on purpose small amounts of disorder, non-magnetic point impurities, and saw how TC decreases. So this axis is the residual resistivity of the normal state. Okay, so it's just the value of the resistivity basically in the normal state, and this is a fit to Abrikosov-Gorkov theory. Okay, and what you get from the fit is that the place where TC disappears is very close to where the mean free path is of order the zero disorder coherence length. Okay, so it's really a textbook example of basically Abrikosov-Gorkov theory at work, destruction of superconductivity by non-magnetic impurities in an unconventional non-S-wave superconductor. Okay, and I think after a few decades and all the upheavals that we saw in the physics of strontium ruthenate, this result really held. Okay, so we are sure that that's a non-S-wave superconductor. Thus the debate is what's the precise symmetry of the order parameter. Okay, so I would really love to see that experiment in this system. Okay, people need to devise a clever way to introduce disorder, a non-magnetic disorder in a controlled way, but I think that would be really interesting. Yeah.
But going back to this idea that your SC2 phase is not going to zero resistance.
Yeah.
Are you already using that as sort of an example of, to say that that's a spin triplet, and therefore it's more sensitive, even though you say you're in the clean limit? I mean,
yeah. Yes.
How are you reconciling
it. It's a good question. Let me come back to that in a bit. Okay, so there just one sentence. One has to distinguish here between small momentum and large momentum scattering, and that distinction would be very important. Yeah.
Just to clarify, so this same mechanism doesn't destroy S-wave superconductivity?
Yes. Yeah. So for an S-wave superconductor, what Anderson's theorem would tell you is that DC should be insensitive. Okay, so ultimately, I mean, if you disordered it enough, it would destroy superconductivity. Yes. Yeah. But that would take much more disorder. Okay, so it's a dramatic difference. The question is, do you start destroying superconductivity when the mean free path is of order the coherence length, or does it have to reach some number times the inverse of the Fermi wavelength, which is much shorter? Okay. All right. So I'm not doing great on time, but that's fine. I'll just discuss the questions and maybe try to address them in the next lecture. That's 10. Yeah. So 0, 1, as in 1 minute. Yeah. Right. So what I'd like to claim. Okay. So the question is, why is the system interesting? Okay. So why do we care about this particular superconductor? It's definitely not high TC superconductor by any measure. So people like to say, well, it's a low TC superconductor, but let's compare TC to the Fermi energy, which is the right scale to compare to. But even by that measure, this is not the highest TC superconductor you've seen by large margin. Okay, so why are these superconductors interesting? Well, in my mind, the reason they're interesting is that here's an example. First of all, okay, two points. First of all, this is a very unusual regime to find superconductivity in. Okay, same for twisted bilayer graphene. This is an extremely low density electron system. Okay, so very unusual from that perspective. So usually we're used to the Fermi level being the Fermi energy being electron volts, the Debye frequency being tens or 100 millivolts, you have this very large separation, and that's something that Andre discussed in great length. This is a very, very different ballpark, okay, very, very, very different animal than that regime. So here the Fermi level is just a few millivolts, okay, and the characteristic phonon frequency is actually comparable to that, okay. You measure, of course, the Debye frequency of graphene is huge. It's the optical phonons in graphene are much, much higher than the Fermi energy here. There may be hundreds, a couple hundred millivolts. But even if you look at the important phonons, which are the acoustic phonons that connect the Fermi surface, they would still be a couple of millivolts. Okay, so the Fermi energy and the characteristic phonon frequency are at best comparable. Okay, and second, here's a system, so the same logic can apply to strontium ruthenate. Here's a system where we really know the normal state very, very well. The normal state is a beautiful Fermi liquid. Okay, this shows these beautiful quantum oscillations. We have very, very detailed information about the normal state. We basically know what the Hamiltonian is. Okay, so sort of even better than quantum materials where you have many, many bands and so on. Here, there's a sort of relatively simple band structure. All the other bands are quite far away. We know perfectly what the Hamiltonian is. What's the superconducting state? Okay, so here's a really nice, I think, test ground for our understanding of superconductivity. So so with that in mind, okay, what I'd like to claim is that there's some puzzles, okay, some important unsolved puzzles. I think there are many regarding superconductivity in these materials, and that's what I'd like to discuss. Okay, so what's the mechanism of superconductivity? Okay, so there's a very natural guess. Okay, so 99%, 99.5% of all the superconductors in the world are S-wave. So why not S-wave here? Okay, and then in particular, we know and love the electron phonon mechanism. Now, as we just discussed, optical phonons are probably too high frequency. Okay, so they would not be able to compete with a strong Coulomb interaction that we know is there. But there are always acoustic phonons that go to arbitrarily low frequencies, and they can mediate superconductivity. Okay, so that's been proposed in a series of papers and studied in quite a lot of detail. Okay, now I'd like to make a little pause and have another puzzle. Okay, so closely related to what Andre told you. Okay, and that Andre explained that if you have Goldstone modes, like acoustic phonons, their coupling to the electrons actually vanishes in the limit of small q. Okay, so that's Goldstone's theorem. Basically, the coupling of anything to a Goldstone mode must vanish at small q. So, sorry?
Adler, not Goldstone. Adler theory.
I see. Yeah. So Goldstone is just the fact that it's gapless. Okay. Yes. Okay. So if that's the case, so now we're really talking about acoustic phonons at the q, which is of order of kf, which is small. Okay. So you would expect sort of acoustic phonons to be very weakly coupled to the electrons. Why are actually acoustic phonons relevant to superconductivity? That's a puzzle I'd like you to think about. Okay, so it turns out that they are important. You can't just throw them out. So what's the problem with this mechanism? Okay, so the first objection we actually already said. Okay, so we know that there are very strong Coulomb interactions in the system. These are the same Coulomb interactions that lead to all this cascade of symmetry breaking phases. These are all driven by Coulomb. We know Coulomb is there. It's strong. And we know that there is not this large separation between the Fermi energy and the characteristic phonon frequency. So how this usual mechanism that we know of retardation, of how the weaker phonon-induced attraction can beat the strong Coulomb interaction, that cannot be at play here. Okay, that doesn't buy you much. So how to beat the Coulomb interaction, that's one puzzle. But there are actually quite a few more. The first, I think the strongest one, purely based on experiments, is this. So if you have a coupling to acoustic phonons, that lead to superconductivity at low temperature, the same electron-phonon coupling in the normal state at elevated temperatures should scatter the electrons. Okay, so it should show up in the resistivity, in the temperature-dependent resistivity of the material. Okay, and that's very well known. That's a Gruneisen theory. Okay, so basically there's a characteristic phonon frequency, which is this theta block Gruneisen, which is simply the frequency of the acoustic phonon that connects the furthest apart points on the Fermi surface. So it's 2kF times the sound velocity Vs. Okay, so that's a characteristic frequency. And what you expect is that once the temperature reaches some fraction of this temperature, of this frequency, okay, which in practice this fraction turns out to be maybe a quarter or a fifth, then the resistivity should grow linearly with temperature with a coefficient which is proportional to the dimensionless electron-phonon coupling lambda. Okay, so that's very well known. This is just a plot of this behavior. This is t scaled by theta bg, and this is resistivity. And you see that already from maybe a fifth of theta bg, you get this linear behavior. And if you just measure the resistivity, you can extract what lambda is. Okay, so now this lambda is basically the same dimension. It's almost the same dimensionless coupling that goes into superconductivity in turn. Okay, so now this has been measured in tri-layer and bi-layer, various experiments. Okay, and indeed, when the temperature exceeds about 20 Kelvin, you start getting this linear growth in approximately linear growth in resistivity over some range of temperature. If you raise temperature further, it stops being linear. Other things start happening, but there is fairly well-defined linear regime, and we know what the slope is. Okay, so the slope of rho over t is maybe 1 to 2 ohms per Kelvin. Okay, so now there's some subtleties here that I won't discuss. There's a geometric factor that's not exactly known, but that's a number of order 1. Okay, we're not doing precision physics here. We're just looking for an order of magnitude. Okay, so from that and from the knowledge of the fermiology, we can extract what lambda is. Okay, and that's a simple exercise, just plugging in the known fermiology. That gives you a lambda which is of this order. So lambda is just small. Okay, and now you compare that to the BCS expression, which tells you that Tc should be the characteristic phonon frequency times e to the minus 1 over lambda superconducting. It's not quite the same lambda. It's you average the electron-phonon coupling slightly differently over the Fermi surface, but typically in many metals, these two numbers are the same within 30%. Okay, so now this is way too small to explain superconductivity in these materials. To get a reasonable Tc, we need lambda to be not smaller than maybe a fifth. If you just plug in the numbers for the smallest Tc superconductors. Okay, so just phenomenologically, from the resistance, it seems like electron-phonon coupling to acoustic phonons is just too weak. Okay, so yeah, usually these two lambdas are close to each other. Okay, and probably out of time. Yeah, so there's another puzzle I'll discuss next time, which is singlet or triplet. What actually determines which state is realized? This puzzle has a slightly more theoretical flavor, but we saw that in the same system, just by tuning density, you can get these two superconducting phases, SC1 and SC2, and one of them is singlet and the other one is triplet. So why is that? Okay, and it would turn out that if you assume electron-phonon mechanism, you would sort of expect them to be the same. Both of them should be triplet, actually. Okay, so all right, I'll stop here.